everybody. Welcome to another UE Systems webinar. We were just joking that it feels like it's been a little bit since we did it. I guess we took the summer off a little bit, but we are back, and actually we've got quite a few lined up that we'll tell you about. But today we are going to be talking about ultrasound made simple, using ultrasound data to support bearing health. And we've got Blair Fraser here who's going to be presenting on it. So those of you that have heard about our on-track smart lube system, we're going to kind of dig in a little bit more about kind of an overview of how that works, but then really dive in on some great success stories that we're seeing and how it's helping folks out in the field get real results. So just some housekeeping before I turn it over to Blair. So we do welcome questions. There's a little questions box, so feel free to type those in throughout the session. I can certainly interrupt Blair and ask questions if you're looking for clarification on something that he's talking about. So feel free to ask throughout, and then of course we'll have some time at the end. We are going to have some poll questions, so there's going to be kind of an opportunity to be a little bit interactive. So we always look forward to at least trying to feel like we're all together, even though we're not really seeing each other and spread across the country and whatnot. We are recording this, so if you have to hop off earlier, if you've got friends, coworkers that couldn't make it, we will share the link out in an email tomorrow, and of course anybody can message us to get the link as well. And then, you know, of course we are doing this live, so if we have any audio issues or anything like that, just bear with us. We'll try and resolve them as quickly as we can. And with that, I'm going to turn the screen over to Blair, and maybe if I can get my mouse here to work. And Blair, we'll let you take it away.
Perfect. Thanks, Maureen. Let me just confirm you can see my screen here.
Yep, we see it.
Excellent, excellent. So yeah, thank you. My name is Blair Fraser, and I'm going to walk us through On Track and kind of what we've learned over the last few years now. It's been about 1.5 years since we've been collecting this real-time data. So it's going to be a little bit of a show and tell, some case studies. Sometimes in these case studies, I'm allowed to use a customer name. Sometimes just for legal reasons I can't, but it sure as heck supported them with some images and some ideas around it. So before I get started, I'm just curious, out of the people that are on this, and Maureen, if we can jump right to a poll, it'll help me out here just to gauge the audience, just to see how much information I need to go in. So I'm just curious, out of those that are on the webinar right now, are you currently using ultrasound? And if so, and when I say ultrasound, I'm not talking about looking at babies, you know, ultrasound in your predictive maintenance program. And if you are, what are you using it for?
All right, so one question at a time. So right now we're getting, it looks like about 73% are a yes, 24-ish% are a no. And so we'll close that one out. And now let's have a look at what people are using it for. And you can pick more than one, because we understand that those that are using it probably are. All right, we're seeing a lot of leak detection, about 75%, 59% saying lubrication, about 40% electrical, 45% steam, traps and valves. So we've got a nice mixture of what folks are using it for, leak detection, and now lubrication getting up to like 65%. So
Excellent.
That's good. All right, cool.
Let's see those lubrication numbers start to climb here after this call. So really, when we look at this, and if you ever attended any of my webinars or I've done a personal presentation for you, I'll always lead with this slide. And I think it's really telling when we look at the data and then the beliefs we need to believe about what is happening with lubrication. Now, the important part about this slide is not necessarily the 80%. It's just, it depends on the study and when the study's done. There's been 2 repeating studies done by the same company that led different numbers, which is okay, right? It might mean we're getting better or worse at lubrication. But regardless if it's 60%, 70%, 80%, the number is still very, very high around what causes premature bearing failure. And where the challenge is when we look at that, we said, yeah, we got to get better at lubrication. But in this case, this study actually broke it down in percentage of what makes up that 80%. And as you see, it's not just what we think around, you know, making sure we're putting the right grease in the right time. There's making sure, obviously, if we're using the right grease, we're keeping it contaminant free. And we actually identify what is the optimal regreasing interval, right? Which is something that has evolved over time, and I'm going to walk us through it. So for those of you that are new to ultrasound, we're essentially measuring two things. We're measuring friction and impact that's happening in that bearing. So when we mount one of our sensors that happens to be part of the on-track system, it's sitting there and listening to that bearing 24/7. It's asking it, hey, what's your friction? What's your impacting? Right? And this goes back to a study from NASA. It's not the best read, but if anybody wants it, I'm more than happy to send it off about, NASA set out to discover what was the earliest detection method of an incipient or early stage bearing defect. And what they came back was the repeatable, most notable change is a rise in the ultrasound level, right? So that's really what drove this technology. So essentially what we're doing is we're listening to friction and impacting in that bearing, and we're constantly waiting to see if we can sense when lubrication is required. And of course, any failure that starts to happen in the bearing itself, any failure starts to happen, it's going to manifest itself in friction, whether it's a inner race defect right here, it's an outer race, cage failure, all of that's going to result in friction. So we can start to tell a lot about the health and needs of that bearing just by looking at the friction. So I'm assuming out of the hundreds of people that are on this call, there's going to be some tribologists, some experts that can probably explain the stribek curve a little better than I can do. So bear with me as I walk us through this. So the stribek curve is named after the gentleman that created this, and essentially what it's looking at is, let's call it friction over viscosity, speed, and load, right? So we're looking at the effective friction. And what the stribek curve is it tells us that there's three regimes, right? The first regime is what's called the boundary regime, and it's not necessarily that you need to know these regimes, but really what this is metal to metal contact. There is no grease, or really important, the oil in that bearing, and the rolling elements are smushed against the inner and outer race, right? So that is the highest level of friction we could possibly get in that bearing. The mixed regime is ideally where we want to be. Now, this isn't drawn to scale because we don't want to be in the upper, the upper left side of this or the lower right side of this. And we look at that dotted line and I'll explain what that dotted line is, but this is ideally where we want to be. And depending on the bearing size and things like that, we want a very, very, very thin film of grease on that bearing. And then this is where it becomes very interesting. If we start to over grease, so we start to over grease that bearing, which unfortunately, from my experience, we do see this more often than under greasing, where a little is good, a lot is better. It's not the case here. So we get into hydrodynamics, which essentially, in my terms, what we're doing is we're shoving so much grease in there, the grease itself has nowhere to go. It's moving in different directions. It's causing resistance from the rolling elements getting pushed around, and we start to get over lubrication. So when we look at the evolution, so we look at the evolution of how lubrication has been done in our facilities over time. And this isn't, again, to a science, it's just really what I see from being in this industry now for 20 years. So the first one I call whenever lubrication. There's different names for it. I'll get to it when I get to it. If I remember, I will go and lubricate this bearing, right? And hopefully there might be some of us on this call that are still doing that, and that's okay. We got you, right? We'll work with you. And then we got really good at taking out a calendar and a calculator and using these formulas that we often don't understand how they came up with them, but we start to plug numbers into them, right? And sometimes they get us into the ballpark, sometimes, and sometimes they don't. And what we have to do is we have to make some assumptions. We're making some assumptions on the humidity in the room, the temperature of the bearing and the atmosphere around it. And I'm located in Canada, and I can tell you this is our last day of summer, both from the season point of view, and tomorrow the temperature is dropping like a stone. So that temperature of any equipment outside is going to be different, right? So we make a lot of assumptions. And then 3 and 4 really came out at the same time. So when we look at condition-based lubrication, is products like our ultrasound, our grease caddies, our 10s, 15,000s, which you essentially use the ultrasound to determine when and how much grease is required. So you're listening to that bearing based on the friction of the bearing, which has proven very, very successful over the years. Now, at the same time, the onset of automatic lubrication, so single point lubricators or distribution systems with the progressive distribution block in it, came out. And they fundamentally solved an issue. They solved the issue of making sure you use the right grease, given you put the right cartridge in it, and it's contaminant free. If you install it right, there's no way for dust and stuff to get in, at least through the grease port. Now, if you have busted a seal or things like that, stuff can still get in. So 3 and 4 really came out at the same time. So what we had from a grease caddy product is really good at determining the when and how much, and the single point lubricators are really good at making sure it's the right grease and it's contaminant free. And I want to say that coming up with this on-track smart lube was some epiphany where we sat in some big boardroom and came up with this idea, but it was really our customers and industry driving us towards this. So what we did is we took the accuracy, precision of using the condition of the bearing to determine when and how much grease is required, and we combined it with the convenience, accuracy of single point lubricators. So essentially, when we're looking at measuring that friction of the bearing, or why would we measure that friction? Because based on that friction, and I'm going to walk you through it, it's not a guess. There are some standards we use, that's an ISO standard, to determine when grease is required. And because we're measuring that grease in real time, we can properly bring that grease down to its ideal friction, bring that friction down to its ideal level, which is an indication of exactly when to stop greasing. So we know precisely how much grease is required. So if we look at it from another chart point of view, if we look at the friction over time, so our friction starts to go up, which is the blue line. Typically, when we see it on condition, is often quite a bit earlier than when it's typically done on time-based lubrication. So that friction has a minimal amount of time when it's actually above its baseline before we'll catch it and apply that grease and bring that friction back down. But what happens now, this is under lubrication. In fact, if I was to draw this for over lubrication, this light blue line would keep on going off the chart because we essentially just keep on adding more and more grease and keep on compounding that friction issue. So if we wait for time-based lubrication, that time where we have an increased level of friction in our bearing is what's causing our bearings to be unhealthy, and that's what we want to stop. So when we design this system, and the first thing there's going to be two things I'm going to tell you about. And one is we are not a grease company, okay? We have partnered and can recommend a lot of grease experts out there, but if you come to us saying, hey, what grease should we use? We're not the right company. The reality is we're here to use ultrasound to determine exactly when and how much grease is required. And now, of course, we can do this automatically with the on-track smart lube system. So when we set out to design this product in our development stages, we said, we have to go to market and learn about these single point lubricators. So before I start to controversially give my opinion and what I've been told about these single point lubricators, and a quick poll for the audience, Maureen, if we can. I'm just curious out there, how many of you are currently using single point lubricators or lubrication distribution systems from a grease perspective at your facility?
All right. It's looking sort of split, 51-49, yes and no. So we're about half and half.
Okay.
Just kind of staying at that. So there you go.
Perfect. Thank you. So when we looked at that and we started to poll our customers saying, hey, are you using these things? We got two answers. Yes, we are. Reluctantly, we still are. And the other option was, I've used them and I'm never going to use them again. And we simply got back to all the answers of why. Why don't you like them? And it came back to an issue with confidence. So what can go wrong with these lubricators? So the first thing is they're autonomous. They're sitting out there in our plants, and we hope that they're doing their job. Even if we know we might be over greasing a little bit or under greasing, at least they're putting grease into the bearing, right? But they're autonomous. So how do we know how much grease is left in them? What if there's a blockage in that grease line, in the grease path coming from that single point lubricator? Right? Now, these are two very, very common issues. In fact, a lot of people we talked to created a time-based maintenance schedule to check these when the purpose of these was to eliminate time-based lubrication. So it's very counterintuitive. And what I'm going to talk to you about next is something that I have been dying to get out there to the world. Now, if you've heard me talk at a recent event, I have talked about this because we wanted to secure that we did actually be able to prove this and file the necessary paperwork to patent this technology. So out in the field, how do we know grease is reaching the bearing? So detecting back pressure is one thing. That is if the grease path is blocked, which can happen. But more commonly was what happens if the lubricator falls off, the remote grease line falls off. There was a maintenance and they've taken the system off, the single point lubricator, forgot to put it back on. Grease lines have been cut. There's many different ways. We wouldn't be able to detect that with back pressure. So we've seen that we've been able to address that specific problem with the Smart Lube logic. And then with this, we can mount it up to 20 feet. So now that we have that confidence, we don't have to be directly on the bearing. We can induce some failure modes, but have confidence that if it was to fail, if anything was to fail with the system, whether it ran out of grease, which it shouldn't happen, if the grease line was clogged, if the grease line fell off, all these different scenarios, we can have confidence that we'll get notified of these situations. So what I'm going to walk you through next is very, very important. Okay, so how do we know grease is hitting this bearing? And we have 8.5 billion data points of us monitoring that friction in real time as it compares to the lubrication status of that bearing. So 8.5 billion data points. Probably now it's 9 since I last looked at the total number of data points. But what we found, and a gentleman at a conference last week told me the correct term. So we've noticed this time and time again, no matter the speed of the bearing, the size of the bearing, there was a phenomenon happening that kept on being repeatable. And once we started to think about it, it became very obvious of what was happening. So don't worry about all the diagrams on here in the wording. So that green dot is essentially, imagine grease is hitting that bearing. Okay, so as grease hits that bearing, it's called the plowing effect. And what the rolling elements have to do is get through that initial slug, that ball of grease coming in the bearing, and how the grease gets distributed around that bearing is through these rolling elements. So if you start to think about it, as that grease starts to get pushed around that bearing, so does the friction, right? If you imagine putting grease into a bearing and one rolling element starts to hit it, well, that friction in that entire bearing is gonna be a momentary spike until it gets pushed all the way around. And we saw this repeatedly. And so what we're able to do is put logic into the Smart Lube system. So no matter how long the remote grease line is, no matter how big, small the bearing is, no matter what the speed is, we look for that repeatable spike. Because what's happening, and this is really different about the on-track Smart Lube system, is when we're measuring that friction, we're measuring it in its normal state about once every minute, which is quite a bit, right? It's quite a bit. But a minute is not nearly enough data or friction values when you start to lubricate. So if you're currently using our grease caddy, you put on headphones or you watch that decibel reading on the screen, and that's your guide for lubrication. So we want to be able to get that real-time information. So the Smart Lube system automatically switches to less than once per second. So we can see the moment grease gets pushed through that grease line, gets down into that zerk fitting, and makes that momentary increase in friction. And that's how we solved one of the biggest problems with these single point lubricators, is knowing that out of all the possible failure modes, a battery died, there's air pockets, just so much can go wrong with these single point lubricators. We know when that system goes to grease, we have confidence grease is hitting that bearing. And that alone, I think, is beneficial enough for most people to start to think about single point lubricators differently. And then how we tie this information now. And why it's important is I'm going to start to talk about a lot of these case studies. So I'm going to show you a lot of screenshots that we've been looking through. And so we've built a platform And again, I promise you I'd say two things that we're not. The third thing that we're not is a master data company. We don't want all of your data going into the platform, right? We are an ultrasound company. We know exactly where our value is and where our core competency is. So when we built this platform, we designed it to get any, and I mean any information out into PLCs, into OSI Pi, into AI systems, whatever you want to get this information into, we'll get it into. But we designed this specifically for remote condition-based lubrication. So we have a real-time friction trend. So hopefully you can see my mouse. If you can't, that blue squiggly line is that friction trend in this bearing. And you'll notice four dotted lines. That green line is the baseline. That's the ideal. If you look at that stribek curve, that's the ideal spot on that stribek curve where we're balancing that friction between the amount of grease in that bearing. The blue, that blue line is the needs lubrication. And what I can tell you is a lot of people start to think about it from a perspective of, well, can I narrow that blue line earlier? And you can, but I can tell you with confidence that the change in that decibel reading or friction level is so subtle, it's not doing secondary damage, right? So we have to balance between how often we're greasing and the level we're comfortable at rising before it greases. So that blue line is the needs lubrication. The yellow is a warning, and the red is a critical. And I'll walk through the ISO standards and how we set those. The other thing we store is all the lubrication insights. So if you can see down here, the last amount of grease was used was 4 cc's. It was 4 days ago. The mode was assist, which I'll tell you what that does. And we also record the baseline friction level, what it started at, and where it ended at. Okay, so we get an idea of this bearing health over time. We get as simple as this health gauge, and you'll see these through all the case studies I'm going to walk you through. So in this case, this arrow is in the green, which is a healthy bearing. Our baseline is 14. This is where we want to see this green line. And you start to imagine this is very customizable. We're seeing a lot of customers that monitor, tens, hundreds of bearings just to create a dashboard just of these gauge widgets because it's easy to walk by and look at it. If this arrow was in the blue, it needs lubrication. And this is where the gamification comes in. So if you can imagine, you start to lubricate, even if you're not using our single point lubricators, and you're just using the on-track to monitor the friction of the bearing, which you can do, and you start to lubricate that bearing, this arrow starts to fall to the left after every shot of grease that goes in there. Guess when you stop greasing? When it hits 14, right? That's when you stop. I've hit the best possible friction level for that bearing. So what happens if, just like on the stribek curve, if you hit 14 and you keep on adding grease, guess what? That arrow will come back. In fact, what we have seen, the rate of rise, which I showed in that chart, is a lot different. So typically it will go, go past the blue and into the yellow. And we have the lubricator status. So we know out there, hey, lubricator, are you happy out there? Are you doing good? I know you're sitting out there on an island all by yourself, all lonely, right? Essentially, it's just sitting there sleeping for the majority of its life. We want to know, hey, when I ask you to lubricate, are you going to wake up and do you have enough grease? Is grease hitting the bearing? So in this case, we probably don't need the decimal point in this, but right here I can say in this system that there's about 80% of grease left in that. You can set up alerts to whatever you'd like to be happy with in order to reorder or fill up that grease cartridge. All right. And then when I look at this, and I've been in the IoT space for a long time, and it's really great to see technology evolve. And what I call the IoT race is the race that who can detect a fault with confidence and certainty the earliest. And it's an interesting conundrum we're in because that's in the predictive domain, right? It's most technology innovation is coming in from that. But what if we were to look a little bit to the left of detecting a failure, and if we start addressing what causes 80% of failures, can we worry less about when we're going to detect an issue, and can we focus just a little more effort on preventing it from happening in the first place? And that's really what I want to challenge you with today. So when we look at this, our business, we're going to hit our 50-year anniversary next year. It's a big year for us. And we look back at all the data we've collected up into the on-track, a lot of it was route-based data. So typically it was monthly data. So what was happening in between those data points was very, very interesting to us. Now with the OnTrack and the OnTrack Smart Lube, we can see down to the minute, and when we're lubricating, down to the second of what's actually happening in that bearing at a friction level. So as I show you all these trends, you're going to start to see, hey, there's a baseline, and that means lubrication is 8 decibels above that baseline. This is an ISO standard, more than, well, I can't share the ISO standard with you, but I can point you in the right direction of where to get yourself a copy of that, or I can walk you through it in more detail. So 8 decibels over that baseline indicates lack of lubrication. The bearing's not hurting. You will not see a temperature change. You'll not see, most cases, you will not see any change in the velocity domain as well. A 16 decibel increase is a failure mode beyond lubrication. And one of the objectives I'm trying to prove to you today is this, is lubrication can temporarily mask or relieve a failure in a bearing, but it can't eliminate it, okay? And I'm going to show you exactly what I mean by showing you a use case of data. And if you see a 35 dB increase over that baseline, that machine is probably talking to you at that point, something you hear audibly. And unfortunately, we've seen people get to that stage where grease can nurse them an extra 10 minutes, an extra hour to get that last batch done or whatever it is. But your future is not looking too good for that bearing. Okay, so what have we learned over 8.5 billion data points? So here's an example of a our sensor, so our Ultratrack 850S sensor. And one thing we have to keep in mind when we look at our sensor is it's the same sensor for every bearing type I'm going to show you. Well, how do we do that? And if you guys are, and most of you are, and we appreciate you are an ultrasound user, you will understand the term sensitivity on your ultra probes. And what essentially sensitivity is, for those who don't know, you can equate it to volume, but it's not really. But imagine you're going out and you're taking an ultrasound or friction reading on a very, very slow speed bearing. That's not producing a lot of energy. So we have to adjust that sensitivity way, way up so we can hear that ultrasound level that's in that bearing. Now you have a big bearing that's moving really quickly. It's producing a lot of energy. So we remove that sensitivity down so we can bring it within a normal range, right? So with bringing confidence into these remote systems, we said we can't go out there and keep on adjusting the sensitivity. So what we did is with our 850S, some of you might be familiar with our 750 sensor. This is a continuation on that technology, which has been proven for decades. What it allows us to do is automatically adjust the sensitivity for that bearing type, for that bearing speed in the sensor itself. So we have contributed to the global microchip shortage by putting a whole bunch more into these sensors, but it allows us to bring confidence. And in fact, I'm going to show you a case study which I didn't think was possible, and I told our team not to do it, which was on just over 1 RPM bearing. And that same sensor worked just perfect. So in this case, we have on a drive end of a belt-driven fan, right? And you can see it right there. It's on a variable frequency drive. So I'm going to talk a little bit about a variable frequency drive and how it affects our data. And you can see there's additional vibration sensor here as well. So what's great about ultrasound is very directional. We're not concerned about movement in a certain direction. So we can get often put on that same bearing with other sensors. In fact, if you look down here, I didn't do this on purpose, but there is another vibration sensor here that's on the structure. I'm not sure how that's going to pick up a bearing fault, but maybe this didn't have room to put it on there anymore. And there is a remote grease line. This copper tube is the remote grease line. So the first few slides I'm going to show you are marketing slides. This is what we typically like to see. So we got that green line behind there. This blue is the friction. And it's very common to see these small little peaks and valleys, 2 to 3 decibels. That's fine, right? That bearing is not going to be, if we ever see, and people ask me, well, what happens if the sensor fails? And with all electronics, eventually they will fail. Our mean time to mean failure is 10, 15 years plus. But when it does fail, it looks like a dead heartbeat, right? It's a flat line. You never want to see if you ever see a perfect flat line, there's no way, even if that bearing it was properly installed, properly lubricated, just babied its whole life, it still won't be a perfect flat line. So this is our way of checking to make sure the center's good, it's tight, and everything like that. This blue line is the lubrication, yellow is the warning, and red's the critical. So this is what we want to see. So in an under lubricated bearing, so here we have one on the drive end of the motor. You can see our sensor here. We can see this is a direct mounted MUE single point lubricator, and it's a full on-track smart lube. So this is, again, this is ideal situation, and this is what I was showing you earlier. So that friction level goes up, and I'm going to show you a use case of how we can tell by the rate of how that friction is going up of what's going on in that bearing. So that friction level went up. Right? At this case, the customer would have received an alert saying bearing 101 requires lubrication. Okay. Or you can get a text message as well. All right. So they had the option. They can go in here and hit Smart Lube Manual. Every time you hit that button, it will dispense grease into that bearing. There's no safeguards in place, nothing, right? And what we really designed that for is for the initial commissioning process, as well as I described, nursing it through failure. If you want to increase your grease consumption, but make sure that bearing still stays alive, you can use that button to do so. Smart Lube Assist applies all the logic. And if you've ever taken our lubrication classes, we teach how to grease using ultrasound or friction as your guide. And essentially what it's doing is we store all the bearing parameters and most importantly, the cavity size of the bearing. And what it's essentially doing is it's looking for, hey, do I have enough grease to even go grease this? So what's my current grease cartridge level at? Does this bearing even require lubrication? If you hit Smart Lube Assist and that current friction is within its baseline, it's going to say, hey, no, I don't need to grease. What are you talking about? Go do something else, right? It's going to word it different than that, obviously. It's going to make sure that friction doesn't go up, because even as we're greasing, if that friction goes up, even though we have not reached baseline, we can still over lubricate that bearing. So if that friction starts to go up, it's a sign of over lubricating. It's going to stop automatically, and it's going to give you that alert, right? And we do have scenarios where no matter how much grease we put in, we'll never reach baseline, because what's happening there's a defect in that bearing, right? And here we can see just how much grease was used, 9 cc's. And I'm going to say this, and I'm going to say it slowly, because what came out of a year and a half, almost 2 years of having the on-track Smart Lube system out is what we found is most bearings require lubrication or required grease more frequently than even we thought, but the quantity is significantly less. And if you talk to any lubrication people out there, they like that, because why? It's constantly refreshing the grease, it's constantly moving that grease. So grease isn't sitting there in a single point lubricator, starting to separate from the oil, from the soap, from the thickener. It's constantly pushing it through, but only when it needs it. So this phenomenon that we saw was really welcomed by the lubrication community. Again, another great case. So here, that friction drops, and you can see, now we can see the time frame here. So each line represents an hour. So this dropped in about 20 to 30 minutes. And what's great about this is it's completely automatic. So you don't have to sit there and watch it do it, but most people do, because it tells you every step of the way. And I do have many videos of the system out there lubricating actual bearings. And if you do want to ever see one, just reach out to me, Maureen, or post a comment here. We'll reach out to, and we can share some of those videos with you. But the rate at which that friction drops is like throwing a stone off a bridge, right? It usually takes a couple cc's of grease, and then it starts to drop just like that. So we can hear, at the time I took in the screen capture, you can export this data to get exact timestamps. It was 7 cc's of grease, which is so small, 7 grams. The baseline friction was 15. We started at almost double that. And if you know the decibel scale, it's logarithmic. So we're, at around a 6 dB increase is doubling the previous level of friction. So we're at 30 decibels, which is quite high. The system automatically brought the friction down within 2 decibels of that baseline, down to 16.7, as you can see, and that's where it stayed. All right, so let's look at the early signs of under lubrication in the bearing. This is one of those aha moments, and only because we have so much data could we come up with this. So a drive end of the motor, it's an on-track smart lube system. It's a VFD. So let me address the question about VFDs. Well, doesn't friction change based on bearing speed conditions? The answer is yes, but on a healthy, well lubricated or properly lubricated bearing, that friction shouldn't change dramatically. So let me show you this. This is a real trend from a customer, right? So you can imagine I just drew an inner race defect with this nice blue explosion that's happening there. If we have a defect and each time one of those rolling elements goes over that defect, we increase the friction, right? It's like a car going over a pothole, right? But now we put that car in a high speed and just turn the wheel to the left and keep on going over and over and over and over and over that speed bump every time, we're going to see it. So if there is a defect in that bearing and it's on a VFD, we can almost certainly match the friction level to the RPM. So if we were to put the RPM, or you have chillers, loads, FLA, the full load amps, and you were to plot it with this, the peaks and valleys just match. So it becomes very intuitive, very simple. That's why people are drawn towards ultrasound, is the simplicity. Is even if you're trying to justify spending on a system like this, or trying to get buy-in for a condition monitoring system, you show someone a friction trend, even a controller, an accountant that you might have to ask for money from, they understand friction. Increased friction equals bad, right? So it becomes very, very intuitive to be able to look at that data. So in an under lubricated bearing, and there's a lot of theory behind this, and again, if there's any bearing experts and lubrication experts on this call, I welcome you to put it into a chat. I can't see it as I have the screen up, but Maureen will let me know. We kept on seeing what we saw these, I call them, if any skiers are out there, moguls, and as a bearing, before it crossed that needs lubrication mark, we started to see the impacting in that bearing start to have more peaks and valleys. And it wasn't until a great thought leader in this space said, I know exactly what's happening there, and was able to show me. We were able to do some experiments about what's happening there. And essentially what's happening is that that grease is degrading, and we start to need to add more grease to that bearing. It's lost its properties. Believe it or not, it's pulling grease from different pockets in that bearing. And this is proven by putting a plexiglass on the outside of this bearing and actually seeing these little micro explosions. And it's hard to believe that there actually is pockets within a perfectly circular bearing, but that's what it was doing, is pulling bearing. And those little explosions that were happening, we were picking up with our ultrasound sensor. It's not every time, but it's very, very repeatable. Before it needs lubrication, as it's starting to get every little bit of grease from that bearing, we'll start to see these little micro explosions happening. It's our first sign that it needs lubrication. Okay, so the reality is what I've shown you now is lubrication under healthy bearings. But some of you, let's just say some, might have some bearings that aren't so happy right now. So what happens in that? So here we go. 9 drive end of a motor is the on-track smart lube system. Now there's a reason I cut this one off. So as you can see here, it went up, customer lubricated, right? It dropped down. It was great. 4.5 cc's. That's so small. A lot of people tell me as I get used to the system, it's like, Blair, that was a round. That's why I used to wipe off the end of my grease gun. Now this is all that bearing needs, right? The baseline friction was 15. Starting friction was 21. It brought it down to 12.2, right? And there's a reason I truncated this screen capture, so it went down. It looks great. But guess what? What happens when you have a defect in that bearing? And I'll go back to my statement I made when I started this. Lubrication can mask or temporarily relieve a friction issue with a defect, but it's not going to eliminate it entirely. And I go back to that pothole analogy. So the city comes by and fills that pothole. It's never as good as the original road. Eventually, as cars, trucks go over it, it digs that pothole out again. It's the same thing that's happening with the grease. So guess what? Here it is extended. That friction went down. But guess what? As those rolling elements smushed that grease and dug it out of that, inner race, outer race defect, whatever it was, that friction level went back up. So I'm not saying we have a crystal ball. We're not going to say you have 2 days, 3 hours and 21 minutes till this bearing fails. But I don't think you need it. All you need to know is, hey, I lubricated, this friction came back. There is something going on in this bearing. Go out there with your ultra probe. Grab a sound recording, do a spectrum, do vibration, do all the technologies that complement each other to figure out what's wrong. But now, without a doubt, you know something is wrong. In fact, we did this a few days apart and said, let's just grease again. Let's see what happens. Guess what? The friction went down, right? But it came back, and it came back a lot quicker than the original one. So I'm not an expert. I'm not a bearing expert. But that's telling me that bearing is getting worse and worse and worse condition as the days go on. Now, this is a really interesting one. And again, I'm not pretending to be an expert here. Okay. And again, the pictures I have of this installation while it was being commissioned, so that the cables aren't connected, but that's not beside the point. And this happened to me personally, so I can talk really articulate about this situation. So they also have ultrasound, and they have accelerometers wired to the outside of this air handling unit. And what we noticed was this, right? Some customers, allow us as UE systems to receive the alerts, and it's just a courtesy thing. As we get them, and in the morning, I take a look at the alerts. I'm like, hey, and before I check my email, I got a call. I said, Blair, our friction in this one air handler went up. I said, whoa. And my first response is, what did you do? Right? And he says, Blair, I haven't done anything. I said, oh, all right. And think about it, what could cause that friction to go up that much? I'm like, oh, unfortunately, guys, it's not looking good. He's like, well, we can't really go and look at it because in the air handling, you got to shut the air handling unit down. It shuts down production, so we can't do that. He says, but I do have accelerometers mounted. I'm like, brilliant. Go take some vibration readings. Go grab your 2140, take some readings for me. And this is what came back. Now, this is verbatim. This is cut and paste from the email. And I know all of you right now, and before this, I gave a presentation on how to effectively communicate and never put something like this in this. But first thing is, this isn't mine. And if anyone knows me, I am an atrocious speller, and I get that. So the spelling mistakes in here are actually from this vibration person, not me, although I can say I probably would have done the same thing. But essentially what he said was, from a vibration spectrum, vibration analysis, he said there's really nothing wrong. There's no mechanical damage with this. The fan and base themselves are in good condition. But if you've ever seen an air handler unit, they have little windows, you can turn a light on and see inside. He said there's a significant, the window was dripping with moisture. So again, maybe there's some AHU experts on here. I'm assuming one of the humidity coils or cooling coils had a leak or something in it. He says, but it's wet in there, right? I said, that's interesting, right? But he said, there's no imminent failure from a vibration point of view. So then we got back to the customer. And I said, you know what? I'm just curious to see what a little bit of grease will do. What happens if we grease that bearing, right? And we did. So we can see here at the time, to the screen capture, 3.6 cc's. And again, we're looking at this from a day point of view. So the reason the blue is so concentrated is because instead of taking data every minute, which represents a dot, we're taking it less than a second when we're going to lubricate, right? So we can get some really good insights from this, right? So we put some grease in and we noticed the trend starting to drop. We took a pause, we did it again, right? And just like that, that friction dropped back down to its baseline with less than 4 grams of grease. So I'm going to stop there and start thinking to yourself, what was happening in that bearing? I have my own theories. So because it's an air handler unit, it's a pressurized unit, is maybe one of the shields or seals broken? Did it suck the grease out? Or did that moisture, if you were to stick your head in there, you would look like it came out of the shower. Because it's pressurized, did all that moisture get into the bearing? And I think we can all agree water and grease is probably not good, right? So by doing this, did we push out the moisture? Don't know. I can tell you to this day, it is still operating. And this was, you can see here, the date, that was August 17th of this year. To this day, that same bearing is operating just at its baseline. So we are going to do some more analysis. Obviously, they wouldn't let me shut down production to be like, I really want to go in there, see this bearing, can you take the bearing out? Let's do a forensic, right? Let's do a grease sample. Let's grab a grease thief. Let's do some analysis, right? He said, yeah, Blair, we'll do that later once we shut down. And I understand that. But what an interesting concept here, which is kind of out of the, you know, a lot of people might not have this issue, but I thought it's very interesting just looking at it from a friction level point of view. And again, I promised you I'd talk about slow speed bearings. I'm sure some of you have some equipment that rotates really, really slow. And if you do, you've already known that ultrasound is really, really good on slow speed bearings. So the team came to me and said, Blair, we want to put the OnTrack Smart Loop system on a 1.8 RPM bearing. That's for making bagels. So first of all, the bagels smell so good. They're delicious. But that's secondary. So we got to make sure these bearings get out there because they're so good. So let's do some tests. Okay, so we put the system on I even said, like, is this thing even spinning? Like, it doesn't look like it's moving, right? And because of that auto sensitivity, and we're the only ultrasound sensor provider that can actually adjust our frequency. So we can adjust that frequency to a range that's better suited for slow speed bearings, which if you use any of our ultra probes, you know that 20 kilohertz works really, really well for slow speed bearings. So lo and behold, we put the sensor on. We had a great reading. That was success number one. I said, let's not celebrate yet. Let's see what happens when we put grease into that. So we put grease into that bearing and the friction dropped. And we've completed this test many, many times. This is a long, long time ago. And we sensed grease many times. And even at a 1 RPM bearing, it still worked. And I'm not sure if you can see my mouse, but just before that drops, there is a faint blue line. There's one data point. You know what that data point is? Yeah, that's grease hitting the bearing. That's what this system is automatically looking for. All right, my last case study, then I'm going to open it up for some questions, ideas, challenges, thoughts. So I've talked a lot about friction, you know, mainly from a lubrication point of view. I showed you what friction lubrication plus a defect looks like, showing you what moisture in a bearing looks like. What about other issues that might not resonate in or be caused by the bearing, but by the equipment itself? Okay, so this customer, and this is a good customer of mine, and they challenged me, and I'm okay with that. So they said, Blair, take a look at this data. I said, okay, what do you think what's happening? I said, and just the way he said it, I'm like, I'm pretty convinced you know what's happening. And he said, absolutely, I do, but I want to see if you can figure it out, right? I said, okay, I'm up for this challenge. So I took a look at the data. So they're identical motors, lead and lag. 1 week they run one week the other, right? I will tell you, this is in the northern climate. In the time this was taken, May, it's still cold. There's still ice on the ground. There's still snow. I hate to say that word, but it exists. So this is motor number one, drive end, non-drive end. The friction level, once it starts, goes up to its happy place and stays there. When they start the other motor, that friction goes up and then eventually comes down. So let's take a look at that timestamp. So this is at 6:52 to 9:52. So, you know, maybe less than an hour. It operates at a higher friction level, but eventually goes down. Eventually goes down. There's no lubrication being added. There's no maintenance being done, but eventually it goes down. So again, not an expert. But I said, this is what I think that's happening. There's something going on with that motor that it has to warm up. It has to start up, and it has to, eventually it finds its happy place. You know what the customer said to me? He said, that's a very untechnical terms you use, Blair, but you're mostly correct. I said, oh, all right. And then he sent me the data from it, right? And again, we see other technologies as complementary. There is not one technology out there that's going to solve all of our problems when it comes to early defects, low speed bearings, lubrication issues. We do believe ultrasound should be your primary, but this is a great example where they use vibration and they saw an imbalance. And essentially, you know, we can read through this. But what was happening because of the cold, and I jokingly say things shrink in the cold, you know, it's really, really cold. But as it started to warm up, that imbalance became less and less and less. thus putting less friction on that bearing. So although it's not a bearing defect, although it's not a lubrication issue, we can still see things that will resonate, manifest into that bearing. Again, not a magic 8-ball. It's not going to tell you exactly what's wrong, but I can tell you what people keep on driving to us for is the simplicity of just looking at this data at a glance. You don't have to stand on your left foot, bite your tongue to the right to be able to look at this data and understand it. So what I'll do is I'll open it up in the last 10 minutes of this presentation. But first, one more poll question, just because there's quite a few of you on the line today. I'm going to be very blunt with this question. Are you interested in learning more about ultrasound and the smart lube? Do you have an application that may be hard to reach, it's really critical, that could benefit from the OnTrack smart lube? And if you do, please go over that poll and just click a yes. I think it's a yes, Maureen, and we'll reach out to you.
There is also a no. We didn't want to lead the witnesses, but yes, there's a yes and a no. But this is
no.
We've got a few, but that's okay. That's okay. Maybe their buddy is saying yes. All right. It's just helpful for us to know so we can be in touch with those of you that want us to be. And we can not bother those of you that don't.
And the reality is too, we have to openly admit the response to this product is more than we anticipated as well. So we do have quite a bit of lead time that we're trying to reduce from our manufacturing effort. So that's why we're really trying to focus on people that would benefit from it and want to essentially experiment with smart condition-based lubrication systems.
You want to do some questions now?
Absolutely, unless they're tough ones.
Well, I don't know.
Okay.
All right, here's one that honestly I'm not sure I've heard someone ask, so I'm going to be curious. So, will this system work on a bearing that's not making a full rotation? We have indexing arms on an oven that are on a bearing, but they only rotate 45 degrees every 10 to 15 seconds.
So the answer is absolutely yes. We've done a lot of linear bearings too, with very short movements with a lot of success. What we have to do is we have to change the way it collects data and how often it collects data. So doing it around, it's not around robin, but doing on a set interval. So what we can do is once it sees movement and then take more repeated data after that. So it's honestly it's something we're experimenting what is the best, but I can tell you we've had a lot of success with linear bearings and bearings that don't go all the way around.
That's fantastic, because then somebody literally asked, have you used this on linear bearings? So that
yes. Again, we stayed away from it at the start just because we're like, let's just focus on things that rotate in a complete circle. But more and more people push us towards linear bearings. So we have a number of use cases with linear bearings as well. Again, depends on the size, the time, length of movement, all that kind of stuff.
Yep. Okay, so how about this one? Have people used ultrasound to check for defects, not lubrication issues, on journal bearings?
Yeah, so when it comes to journal sleeve bearings, typically the prominent technology is like Prox probes, but often at the point where a journal sleeve bearing has friction, you're pretty late in that PDEF curve. So you can absolutely use ultrasound to detect a failure. It depends how comfortable you are with that PDEF curve, right? And often it can be enough to give you enough notice. So it depends on obviously the application, the criticality, but absolutely, if there's a friction issue, even in a journal sleeve bearing, we'll pick it up.
All right, and I believe you covered, the person asked this kind of earlier in the presentation. I'm certain, I know you talked about variable speeds, but maybe just kind of hit it one more time about how this would work in different operating conditions. So not even just variable speed, but temperature changes, things like that. Yeah,
so it becomes I'll give you an example. The project I was working on this week was a large, I'm going to call it a press, a stamper, and presses metal into a bumper. And depending on the bumper size, obviously the gears on the top of this press are going to work a lot different. So operating context does matter. So if we have batch processes that vary and things like that. You have to understand that in the data. And what we'll do is we have different techniques to look at that data, including moving averages and things like that. So we often play with those settings to reduce some of the variability in that data. But it comes down to understanding that context, and that's why we'll need any of these projects we do. We don't just, oh, here's a box and good luck to you, right? It's called our Smart Start. We're there looking at that data with you. We'll provide the ultrasound expertise, you provide the operating context, and together we can figure out what the best way to process that data and display that data and set up the alerts.
All right, talk about kind of harsh conditions, whether it be wet, harsh, temperature, extreme temperature.
Yeah, so I'm going up, if anyone's familiar with the oil sands in northern Alberta in Canada. From a human perspective, it's pretty rough. Mining with the leach tanks and all this kind of stuff. So our the on-track itself is IP68 rated indoor outdoor. The on-track gateway itself gets mounted, typically away from the process units and stuff like that. So what I'm concerned about most is the sensor itself. So again, it's IP68. We can actually now submerge them and put them completely underwater, but they're completely stainless steel and epoxy filled. So water ingress is not an issue. So now we're resorting to, what's the length of the cable, or sorry, the resilience of the cable and things like that. So we have special cables we can use for high temp applications and things like that. And I can't remember off the top of my head, but if that person asked a question, if you want to know the exact details from a temperature range, is, as I said, we go from the desert in Arizona to northern Canada up at the gold mine. So we got a pretty wide range of temperature that we deal with.
Cool. We clearly have a few vibration folks on here, so kind of talk about how you see ultrasound aligning with and playing nicely with vibration, because
yeah, and yeah, no, exactly. And I think it's a great question, and I'm a level 2 vibration, so I understand, and really this is my personal opinion, is see it as they, again, it sounds cliche, but they do complement each other. But there are things that vibration is really, really, really good at, really, really good at. And things that mechanical looseness, soft foot, things like that happen because of the movement. Now, when it comes to the bearing itself, ultrasound is it's challengeably, but if you look at it, there's a recent, I can send it to you, there's another academia paper that was done at a local university where they again studied the incipient fault, and everyone seems to repeat these tests, and I'm happy to see that ultrasound does come out as the earliest. Sometimes it doesn't give enough information to, at that point, to diagnose what the exact issue is, where, vibration, when you start to do all the, you're not going to do an ODS with ultrasound and things like that. So I guess it really depends on what your failure mode you're trying to detect and where it fits in. I can tell you we're going to tie closer and closer. We do see, even in a system like this, if you were to add vibration, it's not going to be as equal from a lubrication point of view as ultrasound, but just having vibration along with the ultrasound data is sure going to give you a lot more information. And I'll say the same to temperature. And the reason I say that is you can start to see where our roadmap is heading, right?
All right, I'm gonna speed round a couple of these. So yes, we were recording this. We will be providing links to the recording. We put all of our recordings up on our YouTube channel, but we will share the link. And yes, absolutely, for those that were asking, you are 100% welcome to share the link with whomever, that's fine. You can have 16 sensors and lubricators to one on-track box. So that was asked a few times as well. Then I think in the interest of time, we do have a lot of very specific questions, Blair. So what I think will be best is we will follow up with those of you that we didn't get to, and even those that we did answer, so we can make sure we fully captured what you were looking for to understand. We'll do that with you separately offline. This product serves does really well being discussed in like a conversation. You know, it's not something that anybody has to come on site for, things like that. So if it makes sense to even dig deeper into some of these really specific application questions, you know, it's easy to do that over a phone call. So don't worry if we didn't get to your question. We 100% will make sure we take care of you. But Blair, thank you for taking the time today. I'm just going to show my screen here for one more second. So those of you that might be interested, it looks like we had a lot of people that answered yes to using ultrasound for leak detection and for electrical. We did just launch last 3 weeks ago or so our UltraView cameras for leak detection and partial discharge detection, and we're doing a webinar on that next Tuesday at 1. So an invite has already been sent out, and we've been posting on LinkedIn and things like that. But if you're interested, you can pop a quick note in the questions box for me to send you the link to register. But if that's of interest to you, we'll be talking about that next week. And with that, we'll just leave our contact information up there. Appreciate people joining in today and being very interactive. Lots of great questions. Really appreciate it. And we will catch you guys later.